we are at the final session of small oscillation. So let's try to do some more problem, and it is a really the next level problem that is not a very routine problem. So sometime if you can encounter this type of problem, how you should approach. So this is the uh, thing we have to learn mainly for the small oscillation. A small oscillation can be adjust in any chapter. It may be adjust in Lagrangian, it may be adjust in Hamiltonian, it may be adjust in your further next chapter, your further next chapter in central force problem, or in rigid body dynamics. Anywhere this chapter can be just introduced, and they can ask that what will be frequency of such a system and which will be a small oscillation. So how we will approach this kind of problem when we have some system. And obviously, we have seen the spring mass system. There is not any problem in spring mass system. The thing will be very much well organized, and we can just develop an algorithm in that system. But sometime algorithm doesn't work. So then, how we will proceed all this kind of problem? So where the ultimate resort is all about the thing is Taylor expansion. The Taylor expansion is the basic backbone of a small oscillation. But where you have to do the Taylor expansion, where you cannot do the Taylor expansion, where you can go up to which level, that are all the prime concern of your small oscillation chapter. So let's talk step by step and why we are doing this, what is the logic behind that. So let's try to do some beautiful problem. So let's go for one wonderful problem, and let's go for potential. And this potential is something given as a v theta 1, theta 2, theta 3, and theta 1, theta 2, theta 3 are the generalized coordinate. And this potential has some k e to the power theta 2 minus theta 1 plus e to the power theta 1 minus theta 3 plus e to the power theta 3 minus theta 2. So this kind of situation is there. So this is given in some functional form. Maybe this kind of potential is there. And someone will ask you that what will be that potential energy matrix if particle is doing a small oscillation, and even I can give you some kinetic energy also. So let's say kinetic energy is T is equal to, let's say, half m L square theta 1 dot square plus theta 2 dot square plus theta 3 dot square. Don't worry, maybe this kind of situation is there. This is potential energy, this is kinetic energy. Kinetic energy is very much straightforward right now. What we have, this is a functional form of potential energy. Maybe this kind of system can be constructed where potential energy is this one. How we will proceed it? How we will proceed it? This is very interesting. Then when you have this functional kind of potential is there, and yes, in one dimension there is not any problem. You can just find the equilibrium point and you can just go for this, and we have done all this. But what will happen when we have more than one dimensional problem, more than 1 degree of freedom? Here theta 1, theta 2 and theta 3 are the generalized coordinates. Now you can proceed it. This is very interesting. So what is the trick? When you have this sort of potential in a functional form, more than one particular potential, what you will do, just go for the Taylor expansion, assuming these all things are very small because we are talking about a small oscillation. And when you are going for the Taylor expansion, go up to harmonic term and neglect the all unharmonic term. What is meaning of harmonic term? Go up to harmonic term means you will go up to square term, and you can neglect the higher order square term, and then you can think, and then you can go for approximation of this potential for a small oscillation or harmonic oscillator. So let's go for Taylor expansion of, and here there is not any need of Taylor expansion. This is a straightforward given into this theta 1 dot, theta 2 dot, and these are dot here. So what we can do, we can just go for Taylor expansion of potential. We can, for Taylor expansion, the first term is K 1 plus theta 2 minus theta 1 plus 1 by 2 theta 2 minus theta 1 whole square plus order of cube. I am just doing Taylor expansion for this. Second, we will go for again 1 plus theta 1 minus theta 3 plus half theta 1 minus theta 3 whole square plus order of cube. And third one is 1 plus theta 3 minus theta 2 plus 1 by 2 theta 3 minus theta 2 whole square plus order of whole cube, and we can just get it. So this is my approximate. We can just neglect all this thing, but this term, you can see here, this term is so symmetric that this theta 1 is cancelled, this theta 2 is cancelled, this theta 3 and this theta 3 is cancelled. So what will happen? There is some constant term. You can just see that there is some constant term, and we can just write all this thing here. So when we will go for the constant term, the K, and inside there is 3 plus, and all this term is half theta 2 minus theta 1 whole square plus half theta 1 minus theta 3 whole square plus half theta 3 minus theta 2 whole square. This is the potential energy. For a small oscillation, this is the potential energy. I can approximate it for the small oscillation. So if it is a small oscillation, you can just go for this. Can you recognize this sort of potential? And please don't bother about this constant. This constant has nothing to do in the force. It is nothing to do in the equation, in the force equation. When you will go for the force, this equation will be 0. So constant have not any role into calculation of angular frequency. Now we can construct the potential energy matrix. So you remember which kind of potential energy matrix will be there?
3 mass in a circle.
3 by 3.
3 by 3 as circle. We have done in the last class, isn't it? So we can just leave this part and we can just go for K by 2. 2 times theta 1 square plus 2 times theta 2 square plus 2 times theta 3 square minus theta 1 theta 2 minus theta 2 theta 1 minus, and you can go for theta 1 theta 3 minus theta 3 theta 1 minus theta 3 theta 2 minus theta 2 theta 3. So you have the same potential in the last class we have done for the circle. Remember, we can have this thing. This will be 2k minus k minus k minus k 2k minus k minus k minus k 2k. Remember all this thing? And you have also kinetic energy. The kinetic energy is half m L square theta 1 dot square theta 2 dot square plus theta 3 dot square. And here you can see that this potential, this kinetic energy is all about ml square 0 0 0 ml square 0 0 0 ml square. Okay, so you can find the angular frequency and instead of m, you can now put ml square here. So there is not any problem. This is all about which kind of system is there and which kind of this problem can be solved. So always remember, what is the last resort? If you have not any a concept, or if you have not any that in the examination, suppose you will be puzzled how you will go for it, the last resort is all about Taylor expansion. So you have to go for Taylor expansion, and you can just solve this kind of problem. I hope we can solve it, and we have seen that we have degenerate frequency root under 3 upon ml square, root under 3 k upon ml square kind of situation will be there. So the thing is that whenever we can just approximate our potential with the Taylor expansion. So if you have any doubt, you can just ask me, then I will go for next problem. Okay, so let's go for next problem. So you remember the problem of moving pendulum, isn't it? Have you remember it or not? So I think you remember the problem of moving pendulum, isn't it?
Yes, sir.
Okay. Okay. So let's go for that problem actually. So what was the moving pendulum? So this was something like that. This mass is m1 and there is some mass m2. Remember all this thing? And here I can take 0 and this angle is theta, isn't it? So we have this all thing. We have discussed all this problem in very detail. I have also promised you that when times come, we will also find the equation of motion for a small oscillation kind of thing. Which kind of motion is there? The M2 will be is oscillating as well as moving. M2 is going, oscillating as well as moving. You can see this is going. So this is moving away as well as oscillating. So what will be angular frequency for M2 for small? Obviously, M1 is just moving with a constant momentum. So there is not any force for M1. So M1 will not do a small oscillation. Which particle will do a small oscillation is the M2. And if you remember, I can have a Lagrangian as half M1 x dot square plus half M2 x dot square plus L square theta dot square, and we have this Lagrangian L square theta dot square plus cross term 2x dot L theta dot cos theta. So this is the kinetic energy, and potential energy is half mg, or this will be m2gl cos theta. Remember all this thing? So if you are not remembering this thing, then you can go for your last class. You can just check it. Where I have taken x1, but I can replace x1 to x, so there is not any problem. So this is my actual Lagrangian. So now, in this Lagrangian, it is said that particle is doing a small oscillation. This is pretty interesting. This is my kinetic energy part. So if you say this is my, I can write this is my kinetic energy part and this is my potential energy part. So how you will go for the small oscillation? So there is two ways. Either you will just solve each and everything equation of motion, then you can approximate. The another way is that you can approximate itself in a Lagrangian, in the kinetic energy as well as in potential energy. Write kinetic energy term separately, write potential energy term separately, and you can just approximate that. So I am doing the first method here. So we will just approximate Lagrangian for my small oscillation. How we can go for it? So look at here, it's a very interesting. Now this is my kinetic energy part. So first is kinetic energy part and second one is potential energy part. So let's go for first potential energy. V theta is actually m2 gl cos theta. So this is my potential energy. For the small oscillation, the theta is very small, but small up to where? Up to what? So what will be this cos theta? This cos theta is m2gl 1 minus theta square by 2 plus order of cube. What we have to do for the small oscillation, we have to go to Taylor expansion up to harmonic term. This is the wonderful thing. This is the one. What is the here generalized coordinate? X and theta. These are the generalized coordinate. Fortunately, X is not taking part into the potential. Only theta is taking part into the potential. So what we can do, we can just go for generalization of this kind of situation. And what will be this particular thing? That V theta is approximately mgl 1 minus theta square by 2. And this is constant term, you will see that nothing to do in the force equation. And you can, if you want, you can write this thing as mgl minus mgl theta square by 2. This is my approximate potential energy for a small oscillation. A small oscillation means I am just ignoring all the unharmonic term such that at least I can solve the equation in a linear form such that my force will be linear. Obviously, if you will go for the next level, the accuracy will be there, but the solving of this problem is very tough. It is very tough how you are going to solve this particular problem when you have cubical term in the potential or fourth order term in the potential. In the next problem, we will see that fourth order will come into the picture, even if we are going to square it up to the second order. Let's see. But right now, you can just go for this potential. So this is my, and please always remember this particular concept. What is concept? That concept is Vij is equal to half, Vij or V potential energy, V is basically half some matrix element eta I eta j. So this eta I eta j is very interesting. And hence, somebody can ask me, sir, why didn't you take this much is also smaller? I can take this one is also smaller. Even theta square will be very small. I can take it. But this is meaningless because I cannot write my potential in this form now. Can you understand what is the basic trick? The basic trick is my potential must be of generalized coordinate square type of thing. This is the basic concept. So in the potential energy, I will go for theta dot square. Now, and what about the beautiful part of kinetic energy? So the beautiful part of kinetic energy is equal to half Tij eta I dot eta j dot. And now you will be surprised that suppose I am, so this is my potential energy. I am writing potential energy separately here. So V theta is equal to, so this will be M2. This will be M2, okay? So this will be M2 GL minus, and this is also M2, okay? M2 GL theta square by 2. Now, so this is the thing I have written. Now let's go for kinetic energy. So I can just remove and I can put this one is my kinetic energy, okay? So this is kinetic energy. I have removed this potential energy part. Now look at very carefully. Here is not any problem. X dot square is there. So I have in this form. isn't it? This is some diagonal kind of thing. Here is L theta dot square kind of thing is there. Yes, I have this kind of thing. Now look at here. Here we have first coordinate. I can say X is my first coordinate, then this is my first coordinate, and theta is my second coordinate. And if I will be go for cos theta, the Taylor expansion of cos theta, then cos theta is 1 minus theta square by 2 and plus theta 4 by factorial 4 kind of situation. A higher order term is 4, cubical term will be automatically gone. Now look at, if I will take cos theta is equal to theta square here, then it will create a huge problem. It will create a huge problem if you will take theta square here, and it will imbalance it dimensionally, as we have concept of this kinetic energy part. What we need only in the kinetic energy is that generalized velocity into generalized velocity. And here is it's already given generalized velocity into generalized velocity, generalized velocity into generalized velocity. I can write this thing x dot, x dot. I can write this thing as theta dot, theta dot. But here x dot and theta dot is there, and if I will put theta dot square, it will create a huge problem. So what is the trick? We will just go for cos theta is equal to 1 into kinetic energy, and we can remove all these part here such that I can represent my kinetic energy in this form. I can represent my kinetic energy in this form. The logic is very much clear. What I want in every small oscillation problem, I want my system will just behave like a spring mass system. That's it. If I am talking about a small oscillation, I need that my equation will be just like a spring mass system, nothing else. So if theta dot will be, if theta dot square I will write here, then it will go up to, it will not go for the spring mass system, it will become a complicated thing. So what we will just go for, I can approximate my kinetic energy also. So what will be my approximated kinetic energy? I am writing it here such that I will write Lagrangian at that point. So what will be my kinetic energy? From the first point I am agreed this is x dot square. The second one is half m2 x dot square plus L square theta dot square plus 2 x dot L theta dot. That's it. I can approximate my potential energy something like this. We can just approximate like this. Now, if you want to construct the matrix, you can construct matrix, or you can just solve the equation of motion. Why you can solve equation of motion? Because there is only x, theta is the only contribution into force, x is my constant thing. So let's go for the solving it by the equation of motion. The one problem I have given you into the assignment, you can solve it by the matrix form also. So I am just solving it by equation of motion. So let's go for it. So if you have any doubt right now, you can ask me.
No, sir.
Okay.
सर
हाँ, yes.
सर हमने एक बार लेग्रांजियन को टी कंसिडर किया पोटेंशियल एनर्जी, एक बार लेग्रांजियन को हमने
नहीं लेग्रेंज ये कहाँ किया? एक बार मैंने पोटेंशियल एनर्जी को एक्सपेंड किया और काइनेटिक एनर्जी को एक्सपेंड किया. अब मैं लेग्रेंजियन लिखूंगा.
ओके सर.
लेग्रेंजियन को एक बार V और एक बार T नहीं, ऐसा नहीं किया. मैंने काइनेटिक एनर्जी लिखा, पहले तो मैंने पूरा लेग्रेंजियन लिखा था, फिर मैंने पोटेंशियल एनर्जी को अप्रोक्सीमेट किया, अब काइनेटिक एनर्जी को भी अप्रोक्सीमेट किया. नाउ आई विल राइट द न्यू लेग्रेंजियन in the approximated form. Okay?
Okay, sir.
So this is my approximated potential energy. This is my approximated kinetic energy. So let's try to write the Lagrangian. is all about T minus V. So this will be half M1 x dot square plus half M2 x dot square L square theta dot square plus 2 x dot theta dot or L theta dot, you can write L theta dot minus. So this will be plus sign here, na? Wait. Mg, what is this potential energy?
Minus, sir.
Minus plus. So this will be plus or this should be minus. This should be minus here.
Minus here.
Huh? What is
Minus.
potential energy? Sorry. Potential energy is equal to minus mgl cos theta. Sorry. M2gl cos theta. Sorry. So this will be potential energy is minus M2 GL2 1 minus theta 2 dot square by 2. So this minus will plus and this will be minus. Okay, don't do it. The potential energy is minus M2 GL cos theta. I have missed this minus sign. Are you
Yes, sir.
comfortable? Okay.
Yes.
So then we will go for this will be M2 GL
Hello, sir.
theta dot square, just a minute, plus M2 GL. Yes, now you can ask.
M2 is below the origin, so we take minus G.
So why I have taken minus sign? Earlier I have just forgotten this minus sign. Okay. I have taken minus sign.
L
Earlier
equal
I
to-
have.
L equal to T minus V.
Arey yaar, L is equal to T minus V. So I have taken this minus sign, na? So this will be minus and this will be plus. What is problem?
Okay, sir.
This is the potential energy. So this will become to minus and this will become to plus. Isn't it? Minus M2GL plus M2GL theta dot square by 2. Now you are okay? Yes or no? That
Yes, sir.
girl who have just asked me T minus V. So this is T
Yes, sir.
minus V. Are you okay now?
Yes, sir.
Okay. Same, I have just do some mistake. I have just forgotten minus sign actually. Okay. So this will be my potential energy. I am just removing all this thing. There is no any need to do this thing. Now, this is also not important. So let's go for this Lagrangian. So this Lagrangian is half M1 x dot square plus half M2 x dot square plus L square theta dot square plus 2 x dot L theta dot. Now minus plus M2GL and minus M2GL by 2 theta dot square. So this is something, sorry, theta square. So this will be theta square. Now let's go for equation of motion. So what we have? First d upon dt del L upon del x dot minus del L upon del x must be equal to 0. You can see del L upon del x is itself 0. So what we have? We have del L upon del x dot is equal to some constant. And we have also learned that earlier also that x is my cyclic coordinate here. So what will be this value? This value is m1 x dot plus m2 x dot, and this term is gone, plus m2 x dot will be gone, L theta dot must be equal to some constant. So this is one equation. I will use this equation afterward. So let's go for second equation. Second equation is most important thing, because what we have to do, we have to go for the equation of motion for theta. And in this direction, you have restoring force as theta dot square. So let's try to go for this equation.
Sir, m2 L square theta dot.
M2 L square theta dot. Okay. M2 L square theta dot. Good. So let's go for d upon dt del L upon del theta dot minus del L upon
Sir,
del
here
theta
M2
is equal to 0.
Sir, here M2 L theta dot आएगा.
M2L अभी
M2
okay
L
okay
theta.
okay ठीक है हाँ M2L theta dot this one is there. Okay good. We are differentiating with respect to x dot. अभी जिस लड़के ने बोला ना उसने confuse कर दिया actually. So let's go for this one. Okay. So this will be, this one is not contributed, only this one is contributed. So this will be M2 L square theta double dot, or you can just go for this d upon dt M2 L square theta dot, and here we have plus M2 L x dot, theta dot will cancel, so M2 L x dot. This M2G has not any role, so this is the first term, and now second term is plus, there is not any x and theta, there is not any theta term, only theta term is there, so minus minus plus M2GL theta must be 0, and now we can just go for differentiating this equation. So this equation I can go for M2 L square theta double dot plus M2 L x double dot plus M2 GL theta must be equal to 0. So now here theta double dot is also, x double dot is also. So we can write x double dot in term of theta double dot. So let's try to find here. So just I can differentiate it. So we have M1 x double dot plus M2 x double dot plus M2 L theta double dot is equal to 0. So from here I can write x double dot is equal to, I write x double dot is equal to minus M2 L theta double dot by M1 plus M2. And now I can write it here, and this equation will be very interesting equation, you can see. So what will be this equation? This equation is M2 L square theta double dot plus M2 L x double dot is M2 L theta double dot by M1 plus M2 plus M2 GL theta must be equal to 0. And now you can see this equation is very interesting equation. I can take M2 common from everywhere, and what we'll get? We will get the equation. I can remove this part only, and here I will
second one
do
is
this
negative,
thing.
sir.
Yes, sorry one. Sorry.
Second one.
Second
M2L,
one.
Yeah, minus.
Here x double dot. This will be minus sign. Okay, this will be minus sign. This will be minus sign. Okay, thank you. So this will be minus sign. What you can take? You can take M2 common, and what you can take L square is also common. So what you have? Theta double dot you can take common, and here is, I am writing M2 and L square I can take also common. So L square also I am take common. So theta double dot L square is common. M2 minus M2 square M1 plus M2 plus M2 G upon L theta must be equal to 0. Now you can just calculate this thing very interestingly. And what you have L square theta and L square is common from everywhere. Theta double dot, this will be M2 square plus m1 m2 minus m2 square by m1 plus m2 plus m2 g by L
Sir,
theta
GLA, sir.
must,
Sir, G
huh?
into L.
G in last term, sir. Last term is G into L.
L square
I have
पूरा
taken
simple
L
में दे
square
रखा है.
common. L square I have taken whole thing from common. Okay. Don't worry. This is common from everywhere. Okay. L square is taking common, then this will come to G upon L. Okay. And you will see the dimension will be very nice. So M square will be cancel. You can take M2 also common. So what will be next equation? So next is we have wonderful equation theta double dot L square and M2 can be common, and there is M1 upon M1 plus M2 plus G upon L theta is equal to 0. And now you can find the angular frequency. And this is nothing but the small oscillation, isn't it? This is nothing but just like a small oscillation, theta double dot plus G upon L M1 plus M2 by M1 theta must be 0. What is value of omega? The value of omega is equal to root under, and this will be M1 G upon L M1 plus M2 by M1. Look at, if I have not done any calculation mistake, I think this will be our answer. So this should be answer. And look at that. This is something like you can see a small, this is something like simple pendulum, isn't it? G upon L kind of thing will become, and this will be some ratio of the masses. So you can have a small oscillation kind of situation here, and you can find the uses of Taylor expansion. You can just do it again if I have done some, I don't think this is any mistake. I remember the answer is something like this. So obviously this is wonderful thing, and look at how you can use the equation of motion. The actual thing in the day one, what I have told you, F is proportional to minus X, and here is also theta double dot, or acceleration is proportional to minus X, or you can say X double dot is proportional to minus X. Then you will go for a small oscillation, and here we have theta double dot is proportional to minus theta, and then we can go for a small oscillation. This is the ultimate thing we have proved by the using a beautiful concept of Taylor expansion. And you remember that I think last day was the Taylor's birthday also. So this is actually all about angular frequency. If you have any doubt, you can just ask me. You can just do the calculation. If there is any wrong thing, if any miscalculation or any error, then I can delete again. But concept is well defined. Okay. So you can see, we can just take the Lagrangian for the whole system, and we can do the Taylor expansion very clever way. And once you will do the Taylor expansion in very clever way, you can find the answer. And you can also do it with the matrix method. I suggest you can just go for the matrix method also. So let's try to do this thing. Okay. Let's go for next problem. Okay. Good. So these all are the advanced problem. These are not very simple problem. And let's go for the one, my favorite problem. This is very simple, but it is very tough to understand. Why it is very tough to understand? Let us try to think. So this
Sir?
is a, yes.
Sir, in the previous problem, if we have to do by matrix method, what will we take v theta we will take that as m2 gl upon 2 theta square. We will put
Yes.
minus m2 gl as 0. Matlab, we'll neglect it. Okay, okay, sir.
If you can find the eigenvalue, I am not sure you can find the eigenvalue of that matrix or not. Yes, you can find the eigenvalue also. That will only one element will be there.
Yes,
Only
sir.
the potential energy. Okay.
Yes, sir.
So just try to do. I haven't tried. But just try to do. Let's see what is happen. Okay. So just try
Okay,
to
sir.
do with, for just what is real problem is there. So this is the beautiful problem. This is K. This is mass M. Let's say natural length is L naught. This mass is constrained to move only in X direction, and let's say this is my origin. So this is my origin. So first we have to construct the Lagrangian, and then we have to just find what will be the Lagrangian for the small oscillation. So first we have to construct the Lagrangian in whole Lagrangian. So first and then Lagrangian for a small oscillation. You can just find this is Lagrangian and Lagrangian for a small oscillation. So let's try to do this problem so what should be degree of freedom? Can anybody tell me?
1.
2.
1 degree of freedom. Nothing to do with this. Who is saying 2? You are still sleeping. How many particle is there? 1 particle is there. And this particle is only moving into X direction. So Y and Z will be 0. So there is only 1 degree of freedom. Don't confuse with a spring. A spring is nothing but the manifestation of small oscillation. Manifestation of oscillation. And the Taylor expansion up to harmonic oscillator is the manifestation of a small oscillation. Nothing to do with the spring to the degree of freedom. Please. Okay. So let's try to go for this is beautiful problem. This is so simple but very complicated to understand. Why this is very complicated? Let me give you answer. Complication doesn't means very heavy mathematics. Complications means you cannot find the answer actually in the direct way. Let's see. So what will happen? This is rigid. So this particle will be here. And this will be my spring. This will be my spring. And this distance is X. I can say I can use another color also. So this distance is nothing but X. This is my X. This is my mass M. This distance is X. Now let's write the potential energy or kinetic energy first. Kinetic energy is nothing but half M X dot square. This is the kinetic energy. Let's go for potential energy. The potential energy will stored into this potential and this is in horizontal plane. So there is not any role of gravity. So this is in the horizontal plane. So I am just leaving this particular gravity. Okay. Now let's try to go for potential energy. What will be potential energy? Half K. And what will be this distance, this length? Can anybody tell me what will be this length? If this is X, this is L naught, this length is what? Of K X square plus L naught square root under minus L naught, isn't it? This is square. Because I just want to write the extension. L naught is natural length. This is completeness. Complete length minus natural length is the extension square. Second one is same thing. Don't worry. So half K, this will be X square plus L naught square minus L naught whole square. So my potential energy will be add up. So both are same. This is the same spring. Don't worry. So what is potential energy? The potential energy is half K. This will be root under X square plus L naught square 2 times. So half will be gone. So this is simple potential energy. And what will be my Lagrangian? The Lagrangian is half M X dot square and minus L naught also whole square. So half m k root under x square plus L naught square minus L naught square. So this is the Lagrangian. I have done first question. Very trivial, very simple. There is not any problem. Now, the actual thing is how to write the equation of motion. And for the equation of motion, for at least for the small oscillation. So let's go for reduce this Lagrangian for the small oscillation. I assume that x is very small for the with respect to some given parameter. And what is given parameter in term of length is only L. So what I can take, so this will be remain same. I can just go for potential part. Let's go for potential part. The potential is V K root under x square plus L naught square minus L naught whole square. What I am going to do, I will take L naught square common. So I can take K L naught square common, and this will be 1 plus x by L naught whole square minus 1. And this is a square also. Now I can just go for small oscillation. X is very, very small than L naught. What I can do, I can just go for the Taylor expansion such that I can write my potential as half Vij eta I eta j. This is the ultimate thing. You must write your potential in this form for the small oscillation. This is the thing you have to always remember. So what we have, the best tool is given by the Taylor, the great Taylor who make our life so simple. So what will be this particular thing? This particular thing is KL naught square, and this will be 1 plus, and you have to go just a harmonic term. So there is no need to go for the first term will be itself 1 by 2 x square by L naught square. The higher term will be 4 term. Then I have leave the higher term. I have get in the first expansion, the coefficient of first expansion is already x square. So I am not going to the next term, and minus 1 is there. This and this will be there. This will be square term. Now, what will be this potential? If you can see this potential very carefully, this potential is Vx is equal to, you can say, this is KL naught square. And what we have 1 by 4 will be there, and you have x4 by L naught 4. And yes, this will be K by 4, and this is x4 by L naught square. This is my potential for small oscillation. Look at the dimension is all about length square kind of thing. Please, this is length to the power 4 and this is length square. So the whole dimension is length to the power length square. But in spite of this, it is huge complication. There is huge complication. You can see this is my potential for a small oscillation. I have nothing to do with the kinetic energy. This is itself in a form of eta I dot eta j dot. So I have nothing to do with the kinetic energy. Let's write it in term of basically that is the Lagrangian for the small oscillation. So I will remove all this part. So Lagrangian for the small oscillation is, so Lagrangian for the small oscillation is
X
half.
by L naught term will also be there, no?
Sorry?
Sir, in when we have taken the approximation and doing the expansion, 1 plus half x by L naught term will also be there, no?
1 is cancel out, na?
Sir, half x naught plus x by L naught.
There is a square term, so it will become 4. So there is L naught to the power 4 here.
So when we are doing the expansion of x square plus L naught to power half.
Array, look at here. What you are doing? You have 1 plus x by L naught whole square root under minus 1. This is only thing.
Yes, sir.
Now expand it. And this is square. This and this is cancel. So what is problem here?
Yes, sir.
Okay.
Yes, sir.
Okay. So this is the same thing. So this will be half m x dot square minus k by 4 x4 by L naught square. So this is Lagrangian for the small oscillation, but it is very dangerous Lagrangian. If you will go for equation of motion, then you have to solve it, and you will just go for d upon dt del L upon del x dot minus del L upon del x must be equal to 0. And what you have to do? You have to m x double dot plus k x cube by L naught square must be 0. And what you have? You have x double dot is proportional to minus x cube. The acceleration is non-linear. Acceleration is non-linear. So what will happen? Is that frequency will constant? No, frequency will not constant. That will dependent on energy. And we have solved this problem when we will go for action angle principle, kx to the power 4. You can take all this thing as something k or some k dash x to the power 4. We have seen that frequency is proportional to 1 upon amplitude, and frequency is proportional to energy to the power 1 by 4. This kind of situation. We have done this problem, isn't it? That what will be frequency? That frequency will be e to the power, I think 1 by 4 or minus 1 by 4 kind of situation is there, or plus 1 by 4. This is plus. Frequency is proportional to e to the power 1 by 4. I think so. You remember this problem when we will go for the.
Yes, sir.
Yes, exactly same thing. So this is non-linear thing. This is non-linear. The system is very simple. It's look like very simple. But when we are going into deeper, we will find it will be complicated, and so complicated. The force is non-linear. And in this problem of moving pendulum, you will see that calculation will be very tough. It will be go lot of calculation, first step, second step, third step. But what we have find? We have find theta double dot is proportional to minus theta. When you will see it, you have to be very happy, because you can easily calculate this type of differential equation. But when you have this kind of situation, then it is really tough for you. And yes, we are so lucky that for the bounded system, we can at least have this particular action angle variable, such that we can find at least how proportionality time period can be calculated or frequency can be calculated. So you can see we have done 3 problems. All problems have different type of thought process, but ultimate thing is all about the final resort is all about Taylor expansion. So this is from my side of a small oscillation. And now you can just go and do this assignments with yourself. And one more assignment, one more problem for the particular double pendulum I have given you into assignment. So I will just discuss in a very brief, because assignment have to do to yourself. What will be potential energy for double pendulum? That will be minus m1 gl cos theta minus m2 gl2. So this will L1, this is L2. We have cos theta 1 plus cos theta 2. Remember all this thing? I think you have done double pendulum. Remember all this double pendulum problem? So this is L1, this is L2. This one is theta 1, this one is theta 2. This is M1, this is M2. So for a small oscillation, what you will do? You will just cos theta 1. You will just go for cos theta 1 is equal to 1 minus theta square by 2. And cos theta 2 theta 1 cos theta 2 is equal to 1 minus theta 2 square by 2. And a higher order term you can neglect in both the thing. And what is the kinetic energy? Remember the kinetic energy? Half m1 l1 theta 1 dot square plus half m2 l half m2 l1 theta 1 dot square plus l2 theta 2 dot square plus 2 l1 l2 theta 1 dot theta 2 dot cos theta 1 minus theta 2. So this is the kinetic energy. Remember, in just go and do the double pendulum again, you will find this kind of situation. So what will be the relevant, what will be calculation here for the small oscillation? What you have to do? We have eta 1 dot eta 1 dot. Yes, we have eta 1 dot, eta 1 dot, eta 2 dot, eta 2 dot, eta 1 dot, eta 2 dot. Then we can just go for cos theta 1 minus cos theta 2 is approximately equal to 1. Not go for theta square term here. We will just go for approximately equal to 1. Then you have kinetic energy, you have potential energy. You can solve it by the matrix method. You can easily solve it by matrix method, and this is your homework. This is in the assignment, and this is the toughest problem you can ever encounter into the small oscillation. If you want to know, first you can do this. If you have any doubt, then we can take it in the doubt session after your test. So we have one more doubt session also for this last test. So we will take it together. So I think you can just go for it. So I suggest you can just go for each and every problem of this particular assignment number. I think you have got the assignment. Yes, you know. This assignment 4, I think you have got. Okay. So just do the assignment. Lot of every question I have discussed directly or indirectly. You can just go and do this assignment. And if you have any doubt, then let me know all of this. Okay. So this is from the my side of small oscillation. So we will finish a level 1 of classical mechanics, and then the two body problem, the rigid body, we will again come to the Lagrangian, again come to the all the thing into next level of classical mechanics. So up to this small oscillation, I will tell this is the level 1 of classical mechanics. Okay. So just do the practice, and then in the second part, we will again go for two different chapter. This is very different chapter. One is the central force problem and Kepler's problem, and another is rigid body problem. And we will again revise each and everything there also. So first, just go and do each and every point here. And if you have any doubt, you can just ask me. And I suggest, I suppose that tomorrow you will give the answer of this particular problem of the double pendulum. Okay.
सर जो आपने प्रीवियस एग्जांपल में x डबल डॉट प्रोपोर्शनल टू x क्यूब लिखा था, उसके आगे फ्रीक्वेंसी लिखी थी ना, वो समझ नहीं आई, दोबारा बताना।
ये समझ नहीं आई। आप लास्ट क्लास किया है एक्शन एंगल प्रिंसिपल क्या क्लास किया था? किया था तो उसमें पढ़ाया था मैंने कुछ। अगर पोटेंशियल आपका kx टू द पावर 4 की तरह रहे, तो इसके लिए स्मॉल किसी भी बॉन्डेड सिस्टम का टाइम पीरियड निकालने के लिए या फ्रीक्वेंसी निकालने के लिए सिखाया था।
यस सर,
सिखाया था। उसी को यूज करना है यहाँ पर।
ओके,
ठीक है, यही तो है ना, यही तो था। अभी क्या था? पोटेंशियल के प्रोपोर्शनल था। पोटेंशियल इज प्रोपोर्शनल टू x4।
सर
यस
सर, ये M2
सॉरी Yes. Mega here acceleration is proportional to positive. No, there is not positive x cube. This is negative x cube. Okay. Why you are saying positive? Mega. Why you are saying that positive x cube?
Okay, sir, now got it.
Okay. This is negative x cube. Minus del v upon del x. Isn't it? Is the acceleration. And even if you will solve this equation of motion, you will get the minus x cube. Okay. Okay. So take care. So I will end this session. If you have any doubt, we can encounter it in doubt session. But before that, you will just give me the doubts. Okay. So I will take the 2 topic of doubt classes. Sorry, 1 classes for the 2 topic of doubt classes after the test of this small oscillation in the Poisson bracket and canonical, as well as this small oscillation phase curve and stability analysis together. So next test is basically for stability analysis, phase curve, and the small oscillation. Okay, and it's a very important test.
Sir.
So yes.
Sir, in the previous question, mu was proportional to e to the power 1 upon 4. If we have to find it in terms of the given
Sorry. What you are saying?
Sir, from action angle principle, we got the proportionality between the frequency and energy. We also have the proportionality between frequency and amplitude. But if we write them in terms of either amplitude or energy, the energy would be there, which is not given in the question. We have to take that.
You listen. If you have this particular thing, if your potential is proportional to x square form of, then frequency will be constant because it is just like a harmonic oscillator. But if potential is something like x4 or even in mod x kind of thing, then this frequency will be proportional to energy or amplitude. Okay. So obviously you have to, if you have to write the frequency, you have to write it in terms of energy. And if energy is not given, then it will be maybe that something wrong from the question side. Okay.
Okay, sir.
Because it's a very obvious thing. For some value of energy, you are finding the frequency. Even in this case also. But unfortunately, here frequency is not dependent on energy. Okay.
Yes, sir. I was just telling that like the previous questions, we had the answer fully in terms of L, G and M. But in this question, we cannot do that. We have to put in energy.
Yes,
that is what I was pointing out.
If you are using this action angle principle, first of all, directly you cannot solve this thing. Okay. Directly from the equation of motion, you cannot solve it. So what will be next resort? What will be next thing? Next thing you have to go for the action angle principle. And if you are using the action angle principle, you have to give the answer in terms of energy or in terms of amplitude according to problem. Okay. Are you getting this? Hello? Okay. I think she lost contact. Chalo. So take care and study hard, है ना? अब tough study शुरू कीजिए.